Welcome everyone. My name is Philipp Allgeuer and I'm from the Knowledge Technology Group in Hamburg. Today I will be presenting our work on achieving truly unconstrained open vocabulary image classification. So let's dive right in. Our core motivating question is this: how can we determine what is contained in an image without knowing any context and without any restrictions? This is, for example, relevant when working with arbitrary web images, the vision system of a household robot, anomaly detection, or similar. Existing methods generally require either an explicit prompt or category query, a predefined or inherent list of candidate classes, a training step on a dataset of limited cover like Elvis or CC3M or CC12M, or very large compute, response time, hardware requirements and such. Here I'm obviously referring to multimodal LLMs, which are not suitable for real-time vision applications, as image classification should be fast and energy efficient. To this end, we propose Novik, an approach where input images are first encoded by a high-performing clip model and then generatively decoded as an object classification label using a newly trained so-called object decoder. This decoder exclusively receives the clip embedding vector as input, and as output simply produces the best matching object noun it can. You can think of this whole architecture as efficiently chaining a clip image encoder with an inverse of the corresponding text encoder trained for the specific task of object prediction. Given an image and nothing else, Novik can generate an accurate, fine-grained textual classification label in real time and with equal coverage of the vast majority of the English language. Novik is extremely efficient to train because it uses text-only supervision and is very scalable and customizable as it only uses text from synthetic data sources. An exhaustive dictionary of English object nouns was constructed and used to generate caption-object text pairs via prompt templating. A caption like "a cartoon, clock and chandelier and hammock" is encoded offline using a clip text model, has some noise added online, and is used to train the object decoder to output either clock, chandelier, or hammock. Some additional caption object pairs were supplemented via LLM generation, like for example the caption "birds gathering around the bird feeder for a meal," which is expected to map to the object noun bird feeder. At inference time, zero-shot transfer is performed from text to images. Instead of using text embeddings, the object decoder is inferenced directly on clip image embeddings, producing the desired object noun classifications. As a side note, the zero-shot transfer from text to image embeddings is actually completely non-trivial due to the so-called modality gap, which is huge. Recall that two completely orthogonal vectors are 90 degrees apart. It can be tested for clip models that matching image text pairs can easily, on average, be 84 degrees apart in the embedding space, and rarely much less than that. The strategies used to overcome the modality gap, including in particular multi-set training and careful design of the noise model, are discussed in detail in the paper. So here is a close-up view of the object decoder. We can see that the input embedding vector is linearly projected to form a number of prefix tokens, which are combined with the text tokens in an autoregressive text transformer style. Learned positional and token embeddings are used in addition to full attention to the prefix tokens at all sequence locations. Altogether, the object decoder has around 12 million trainable parameters and is trained on a dataset of 52 million captions, which corresponds to around 92 million object noun targets. This takes 1 to 3 days on a single RTX A6000, which is quite impressive considering that up to 1.7 billion samples are being seen over 18 epochs by a single GPU. This is extremely efficient. To put this into perspective, training 18 epochs of ImageNet 1K in exactly this way yields 88.2% accuracy in only 19 minutes. This top 1 accuracy is actually not far at all behind state-of-the-art performance. Clip model included, at inference time, Novik only requires at most 5 GB of GPU memory and 7 to 26 milliseconds per image depending on whether a batch size of 1 or larger is used, making Novik resource efficient and definitely real-time. Evaluating a cross-modal system that can output arbitrary object nouns of the English language is not trivial. We could always just evaluate Novik on classification benchmarks like ImageNet 1K and Food 101, but for this to be fair, we need to artificially restrict the beam search to just the defined classes. This works, but is not ideal because it, amongst other things, forces the model to choose object nouns that it doesn't even think are best. So classification benchmarks can give us some idea, but are in general a significant underestimation of Novik's capabilities, as we show in the paper. To tackle this problem, we curated 3 new evaluation image sets specifically for open vocabulary image classification: the World, Wiki, and Val3K datasets. The World dataset in particular tries to include diverse, atypical, deceptive, and indirect objects in order to ensure a challenging and meaningful evaluation. Given Novik's predictions on one of these image sets, human and LLM annotations are performed, which we denote with a suffix like WorldH and WikiL. Note that it is clearly completely infeasible to annotate all possibilities in advance. Let's take this image as an example. Suppose we give this image to Novik and get back that this is a Rhodesian ridgeback. We then assign one of these 5 annotation categories depending on the correctness of the prediction and whether the prediction refers to a primary or secondary element of the image. The corresponding number of points awarded are then shown in the right-hand column. The prediction score for an entire image set is then the mean amount of points per image as a percent. If we count secondary predictions as incorrect, then the resulting score is referred to as the primary score. If alternatively we halve the points awarded to predictions that are overly coarse, then we get the overall score. This would penalize generic model predictions like, for example, dog in this case. Note that the LLM annotations only cover the categories required for calculating the primary score. Here are the results of Novik for clip models of various sizes and strengths, alongside a number of other ablations regarding frequency threshold, dataset composition, and noise parameters. For starters, we can see that the human and LLM annotated scores on the Wiki image set are largely well correlated, and that as expected, the WikiL scores are somewhat lower because they are primary scores that don't count any secondary predictions. The LLM is also quite strict, yet at the same time sometimes makes its own mistakes. We can also see that the prediction scores of Novik consistently increase as stronger clip models are used, exceeding 87% performance on WorldH. 87.49% is actually a strong result, considering the model must work for any conceivable image and without any contextual clues. In order to achieve such a result, Novik regularly makes correct predictions as detailed as red velvet cake, Brazil nut tree, electron microscope, and Egretta caerulea, which is a bird, by the way. As described at the beginning of the presentation, to our knowledge, no directly equivalent related work exists, or at least existed at the time of publication. So we compare against tag-to-text and the Recognize Anything model, also known as RAM. These models require explicit class candidate lists, making them neither prompt-free nor unconstrained in terms of the English language, and are furthermore trained on datasets of limited cover. The process of training is also significantly slower as it is not text only. So there's a lot to unpack in this table, but most prominently we can see that tag-to-text and RAM have particularly low primary and overall scores relative to their prediction scores. This indicates that a major part of their prediction scores undesirably comes from coarse and secondary predictions, which by contrast is not the case at all for Novik. This results in Novik leading by up to 24% absolute, which is the difference between 64% performance and 88% performance. Here are 2 plots showing how frequently the most commonly occurring object nouns are predicted for the WikiH dataset in descending order of frequency from left to right. In the left plot, we can see a comparison between RAM, tag-to-text, and Novik, where we can identify that RAM and tag-to-text have a very peaked frequency distribution, corresponding to just a small collection of words that are reused over and over. In fact, just the top 20 words used by RAM account for around 1/3 of all images in the dataset. This is not the case at all for Novik, which has a more uniform distribution spread out over a much larger base of words. The right plot shows a zoomed-in view of the top 10 words for RAM, where we can see their coarse and uninformative nature, like man, tree, flower, plate, and grass. These words are easy go-tos that often avoid the actual classification task, like for instance what is on the plate or grass, or what type of tree or flower it is, or what object the man is using. When applied to the ImageWolf dataset, for example, RAM and tag-to-text both just predict dog 88% of the time, and never a single dog breed. Novik, on the other hand, predicts 90+ dog breeds with a high accuracy. This highlights the severe lack of diversity and specificity in the predictions of RAM and tag-to-text. The difference in performance between Novik and the related works can easily be seen through qualitative examples. Siglip Novik here is using a smaller, faster clip model, while DFN5B Novik uses a slightly slower but higher performing one. In general, it can be seen that RAM frequently misses the main point of images, like predicting man instead of banknote, or predicting hand instead of hearing aid, which is clearly the focus of this image, or car instead of roof rack, or in this image, predicting palm tree instead of referring to the lamppost with the wreath, which by the way I had to look up, but is genuinely located in Florida Key, as Novik suggests. Here, the S means that it's a correct secondary prediction. In general, it can also be seen that RAM and tag-to-text provide coarse labels, like cake instead of red velvet cake, or flower instead of daffodil, and panda instead of red panda or ailerus. And I mean, panda is theoretically correct, but most people would be expecting something big, round, black and white in that case. The second last image here is an interesting case where Novik is actually able to determine that this is a stuffed toy representing a Staphylococcus microbe. That feels a little bit absurd, but is explainable by the German word Staphylokocke being visible in the image, even if not prominently. Indeed, if we blur this text out, the DFN5B Novik actually falls back to stuffed toy like the other Noviks predict. Many further qualitative examples can be found in the paper. So to summarize all we've seen in this presentation, we can say that Novik is generative as it produces free-form text labels, unconstrained as there are no candidate classes, open vocabulary as it is trained on a full English dictionary of object nouns, text-only trained as no images are required during training, efficient as it trains in only 1 to 3 days on a single GPU, real-time as it takes only 7 to 26 milliseconds per image for inference, reliable as it achieves performances of up to 88%, scalable as the performance scales well with the underlying clip model, and last but not least, open source, with the code on GitHub being able to fully reproduce the results. To summarize our contributions, we contributed a novel open vocabulary object decoder training scheme that is fast and text-only, as well as exhaustive and controllable in terms of the coverage of vocabulary. We also created and released the object noun dictionary, created 2 new large-scale synthetic caption object datasets, one prompt templated and one LLM generated, and curated 3 new image sets for the evaluation of open vocabulary image classification, including the establishment of associated metrics. And with that, I would like to thank you for listening.